Everyone, this is Sopan. Today I'm going to present our work Understanding Hessian Alignment for Domain Generalization, a joint work with Gojun Zhang, Amir Esteri, and Shi Chen. The main result of our work is that the distance between classifier head Hessians is an upper bound of the transfer measure, which is a recently developed tool for quantifying the domain shift. So basically, in this plot, if we consider blue and red curves as classifier head Hessians, this dark line is a transfer measure which quantifies the domain shift, and is basically the difference between the excessive risk of on-target and source domains. So intuitively, if we align the Hessians or curvatures for these two curves, we will have less transfer measure, and as a result, better transferability and better out-of-distribution generalization. So we also show that Hessian and gradient alignment simultaneously encourage different level of invariant representation learning for losses, features, and features covariance. And as a result, this is a generalization of many other works. To align Hessians efficiently, we also propose two simple methods that align the Hessians with less computational overload. So basically, let's start with some preliminaries. The transferability means every near optimal source classifier is also near optimal on target domain. And the transfer measure to quantify the transferability is basically the difference or the worst case scenario of the differences between the excessive risk on target and source domain. So under some mild assumptions, we show that the spectral norm of the Hessian difference between source and target domain is an upper bound for the transfer measure. Further, we show that aligning Hessians and gradients can align different attributes, as I mentioned, in terms of error weighted by feature, logits weighted by features, and logit weighted by covariance. And each of these attributes or similar to these attributes have already been proposed in other invariant representation learning techniques. These tables summarize these algorithms. So as you can see, doing Hessian gradient alignment simultaneously align different attributes in terms of covariance, features, logits, and error. And as a result is a generalization of other proposed techniques. To align Hessians and gradients, we propose two techniques, namely HGP or Hessian gradient product and the Hutchinson. The HGP align the Hessians indirectly by aligning the multiplication of the Hessians and gradients. So we assume that if the gradients are aligned, to align the Hessian and gradients, we need to also align the Hessian needs to be aligned. So the interesting point here is that the Hessian gradient can be calculated easily using just two backpropagations. For the Hutchinson, we use the Hutchinson estimator of the main diagonal of a matrix to estimate the main diagonal of the Hessians and then align them. In terms of the result, this table shows our result on color MNIS with the setup same as invariant risk minimization paper. So as you can see, Hutchinson and HGP achieves very good performance. More precisely, Hutchinson achieves the state-of-art result on the target domain. We also achieve very good performance on the domain-based benchmark for VLCS, PAX, Office, Home, and DomainNet datasets. We also have some experiments for the transferability, which is measuring the out-of-distribution accuracy after perturbing the classifier head for models trained with different domain generalization algorithms. As you can see, HGP and Hutchinson consistently keeps their performance even if after we perturb the classifier heads. This plot shows the training dynamics for the color emission experiment. As you can see, at epoch around 200, when we increase the regularization parameters, the Hessian distances reduce and the out-of-distribution generalization increases. Eventually, this is the adversarial robustness plot that shows that if we apply fast gradient sign method, the algorithm trained with Hutchinson and HGP consistently keep state performance. Thank you so much.